Hi everybody. You're watching the video for section 10.1, which is an introduction to Boolean algebra. George Boole recognized that a lot of the principles of logic that we've been using had a lot of similarities to algebra, and he was able to build a type of algebra which is a little bit different than what you've used before, but perfectly represents the same logic principles that we've developed, and it allows us to take complex logic statements and simplify them. We're going to do that using Boolean algebra and using logic circuits over the next few lessons. But let's go ahead and look at what Boolean algebra is and establish some of the basic principles. Boolean algebra applies an algebraic principle to the logic that we've already built. Using logic, we would say that every condition is either false or true. In Boolean algebra, we don't use those statements. We say that if a condition is not met, we call that a zero condition, but if a condition is met, then we call that a 1. Conjunctions, or AND statements, are represented by what looks like an upside down V or a caret. Conjunctions in Boolean algebra are represented by a dot, which is like the multiplication sign in regular algebra. Disjunctions we represent with a symbol that looks like a V, but disjunctions in Boolean algebra are represented by a plus sign. So multiplication signs in Boolean algebra mean AND, addition signs in Boolean algebra mean OR. In logic, we use a tilde to represent a negation. In Boolean algebra, we put a line over our condition to show negation. And just as we used truth tables to show our outcomes, we're now going to use what are called Boolean tables to show our outcomes. So let's get started. The first thing we need to do is consider what the outcomes for addition, Boolean addition, that is, or Boolean multiplication are. So we're going to make a Boolean table, which is just like a truth table for each of these things. So to make this Boolean table, we would start out the same way, but we're not going to have conditions P and Q. We're going to have conditions A and B. And as we did before, we can list every possible combination of those conditions by listing 2 satisfied conditions for A and 2 unsatisfied conditions, and 1, 0, 1, 0 in the B column. That's every possible outcome for A and B. So let's see what the outcomes of A plus B are in Boolean algebra. Now remember, addition in Boolean algebra is a disjunction. So we're really looking at the OR condition here. So do we have A or B met? We do. We have 1s in both of those, so we have both of them met. So yes, we have one or the other. In fact, we have both. In the next row, we have 1 and 0. Do we have A or B? Yes, we do. We have A. In the third row, do we have A or B? Yes, we do. We have B. But in the fourth row, do we have A or B? No, we don't. And so we have 3 1s and a 0 in the A or B column. That means we can fill those results into our addition multiplication table, and we can conclude that 0 plus 0 is 0 in Boolean algebra, 0 plus 1 is 1, 1 plus 0 is 0, and 1 plus 1 in Boolean algebra is 1. Let's do the same for the multiplication table. We'll add another column to our Boolean table and consider A times B. Multiplication is the same as a conjunction, so in order to satisfy the A and B condition, we have to have both A and B conditions met. Row 1, we do have both A and B having 1s. Row 2, we don't have both. Row 3, we don't have both. And in row 4, we don't have both. So that means we can complete our multiplication table. And when multiplying using Boolean algebra, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. That happens to mimic regular old multiplication. Okay, let's use those multiplication and addition results to evaluate each of the following Boolean expressions. Our first one, we have 0 plus 1 times 1 plus 1. Well, from the results we just saw, 0 plus 1 using Boolean addition is 1. 1 plus 1 using Boolean addition, remember that's OR, and we do meet both conditions, so the disjunction is satisfied. And we're going to multiply those two results. And 1 times 1 is 1. So the result of that Boolean expression is 1. For the expression on the right, we have 0 times 1 plus 0 plus 1. And just like regular algebra, we start with parentheses and work our way out. So the inside parentheses, 1 or 0, 1 plus 0, that is 1. Once we get that result, we have 1 plus 1 in Boolean algebra, that is 1. And then we have 0 times 1 in Boolean algebra, which is 0. And so the result of that expression is 0. Okay, you take a minute and see if you can use Boolean algebra to simplify the expression on the bottom of your screen. Pause the video, work that out, and we'll work through the solution. Okay, let's simplify this expression. We'll do all of our inside parentheses first. In Boolean algebra, 1 times 1 is 1. That takes care of that parentheses. In Boolean algebra, 1 times 0 is 0. And 0 times 1 is 0. Now let's clean up the contents of our brackets. 0 plus 1 in Boolean algebra is 1. And 0 plus 0 is 0. And in Boolean algebra, 1 plus 0 is 1. So the result of your simplification should be 1. Okay, the distributive property works in Boolean algebra just the same way it works in traditional algebra. So let's see how that shakes out. Let's create a Boolean table to show that the operation of multiplication distributes over addition. So for starters, we'll create A, B, and C columns to represent all those possible conditions. And just as we did with truth tables, we'll represent all the possible conditions using the same pattern. A will have 4 1s and 4 0s. B will have pairs of 1s followed by 0s. And C will have individual 1 followed by a 0 repeated. That'll represent all the possible conditions of A, B, and C. So to start building the left side of our equation, we want to have A times B plus C. Let's build a B plus C column. So remember, this column is going to be satisfied when we have condition B or C. So in row 1, we have both B and C being met. Row 2, we have B but not C, so that's a 1. We do have condition B. Row 3, we have condition C. Row 4, we have neither condition, 0 and 0, so we don't have either, so our Boolean result is going to be 0. B or C in row 5 results in a 1. B or C in row 6 results in a 1. Row 7 we have C, that's a 1. But again in row 8 we have neither, so that's a 0. Now that we have a B or C column, we're ready to build A and B or C. So we're looking at column A and column B or C. We have to have a 1 in both columns for each row in order to meet A and B or C. So in row 1 we have A and B or C, which results in a 1. In row 2 we have A and B or C, which results in a 1. And in row 3 we have A and B or C, which results in a 1. But in all the remaining rows we're missing one of the two conditions. In A we have 1, but no B or C, and so that's a 0. And then for all the rest of the rows we're missing condition A. So we have 0 for A and B or C. That completes that column, and that represents the left side of our equation. Now let's build the right side of our equation. Okay, let's start building the right side of our equation with an A and B column. And the only two rows where we have conditions A and B met are row 1 where we have A and B, and row 2 where we have A and B. Anything beyond that we're missing one or the other. We're missing condition B in rows 3 and 4, and then we're missing condition A in all the rest of the rows. So A and B consists of a 1, 1 followed by all zeros. So let's build the A and C column. A and C is satisfied in row 1 because we have condition A and C. In row 2 we're missing condition C. Row 3 we have conditions A and C. And in all of the rest of the rows we're missing condition A or C. And now we're ready to build the whole right side of this equation, a and b or a and c. That is to say a times b plus a times c. That means, of course, that we're going to be looking at our two previous columns, the a and b column and the a and c column. If we have the condition of either of those met, since this is addition or an or, the disjunction, we'll have a 1 in that row. And if you fill in that column, you'll find out that we get 1, 1, 1, because we have a and b or a and c only in the first 3 rows. Everything beyond that, we have neither a and b or a and c, and so we have zeros below that. Once we complete that table, we can compare the left side of our equation, a times b plus c, and the right side, a times b plus a times c, and you can see that those columns match perfectly. 1, 1, 1, 0, 0, 0, 0, 0 in both cases. That means that they are equivalent statements, and that means that we can distribute multiplication over addition. We'll get the same result just like traditional algebra. Now let's look at a similar result. As it turns out, we can distribute addition over multiplication. That is not true in traditional algebra, but it does work in Boolean algebra. So we're going to show the same result using a similar process, although I'm going to streamline it a bit in the explanation. So of course we'll start by building conditions a, b, and c and all the possible combinations. Now let's start building the left side of this equation. So we built the b and c column. You can check each one of those rows for yourself to verify that we get 1, 0, 0, 1, 0, 0. And we can build an a plus b times c or a or b and c column. 1, 1, 1, 1, 1, 0, 0, 0. Now we're ready to build the right side of that equation. So we can build an a or b, that is to say a plus b column. Now we'll build an a plus c column. And there, we've built our a plus c column by checking conditions a or c. And we have 1, 1, 1, 1, 1, 0, 1, 0. And finally, we can build our final column, which will represent the entire right side of the equation. Since we're checking the a or b column, or the a or b condition, and the a or a plus c condition, and we need both of them, since this is a conjunction or multiplication, our first 5 rows all result in 1s because we have both conditions met, but our bottom 3 rows result in 0s because we do not have both conditions met. And so we're ready to reach our conclusion. So since our left side of the equation, the column that represents a plus b times c, is a 5 1s and 3 0s, matches the right side of our equation, a plus b times a plus c, has the same sequence of 1s and 0s, they are equivalent statements. That means in Boolean algebra we can distribute the operation of addition over or into a set of parentheses that contains multiplication. And we would get a plus b times a plus c. That again, that's not true for regular algebra, so as we move forward that's going to be a tricky thing to watch for, because at this point you've been trained in your life that that doesn't work, but suddenly with Boolean algebra it does. The last thing that we want to do are write Boolean expressions that yield particular results. And there's going to be some real value in that in the next few lessons, so that's the next thing that we want to do here. We would like to write a Boolean expression that yields a 1 when a and b are different, and a 0 when they are the same. So we'll start by listing all the possible combinations of a and b. Now to build these conditions we're going to have a negation. Ultimately we would like to have a result of 1 when a and b are different. That would be rows 2 and 3 here, they're different. And we should get a result of 0 when they are the same, that is to say rows 1 and 4. So it will be useful here to look at the negation of a and b. So let's build another column with the negation of a and b. Now in Boolean algebra we represent negation by putting a line over our condition. So we have condition a, and here we have the negation of a. And we also have b and the negation of b. So the negation is simply going to be the opposite. So the negation of a will be 0, 0, 1, and 1. And the negation of b, since b was 1, 0, 1, 0, the negation of b will be 0, 1, 0, 1. Those negation columns are going to be useful because they give us a way to describe when a and b are different. So for example, in row 2, there's a case where a and b are different, but if a and b are different, then that means a and the negation of b are the same. So we want a column that represents a and the negation of b. That is to say a times b, and you'll notice here that we don't have to use a multiplication symbol there. Just like regular algebra, we can put them next to each other, and that implies multiplication or a conjunction or the and condition. So a and the negation of b, a and the negation of b in row 2, that puts a 1 in row 2. All the other rows, though, will yield a 0 in that spot, because we don't have a and the negation of b being met in any of those. Now that column gives us one row in which case a and b are different, but row 3 also has the conditions of a and b being different. And so we'll have, since we don't have a but we do have b there, we would have b and the negation of a. So we'll build a column that represents the negation of a and b. That allows row 3 to have a positive condition. The negation of a and b are met. But we'll have zeros everywhere else. And finally, we now have row 2 representing where a and b are different, and row 3 representing where a and b are different. And we have those two conditions represented here. As long as we can have either one of these, we should have a positive output. That's what our original challenge was, to write an expression that yields a 1 when they are different. So our last column is going to be a and the negation of b, or the negation of a with b. That's going to be a 0 in row 1, a 1 in row 2, since we have a and the negation of b, a 1 in row 3, since we have the negation of a with b, and a 0 in row 4. And that meets our original challenge. Our Boolean expression yields a 0 when a and b are the same, such as the case with row 1 and row 4, but it yields a 1 in rows 2 and 3 where they are different. Okay, here's the last problem in this lesson, and a challenging one for you to take some time to practice. Try and create a Boolean expression that yields a 1 when 2 of the 3 parameters a, b, and c are met, and 0 for all other conditions. Give that a try. Pause the video and unpause when you're ready to see the solution. But here's a hint. You're going to build this very similarly to the way that we built our last example. You'll have an a, b, and c column, but then you'll also have a negation of a, negation of b, and negation of c column. Okay, let's have a look. First of all, we'll need an a, b, and c column to represent all those possible conditions. And as I suggested, let's also build those negations so we can use those as we work towards our Boolean expression. So, everything that's in column A will be reversed. Since we do have condition A met in row 1, we'll have a 0 in that spot for the negation of A, and so on. And now let's build the negation of B and the negation of C. Now we want to write a Boolean expression that yields a 1 when exactly 2 of the 3 parameters are met. That means we want to have A and B but not C, A and C but not B, or B and C but not A. So let's build a column for each of those conditions. Here's one case that will yield a 1 when we have 2 of the 3. That is to say, we have condition A and B but not C. In other words, we'll have A and B and the negation of C. So take a minute and look, where should that 1 occur? A and B but not C? Yeah, row 2 has A and B and not C, or in other words, A and B and the negation of C. So in the next case where we'll get a 1 result is if we have A and C but not B. There's 2 of our 3 conditions, A and C but not B. Where will we get a 1 in this column? We'll get a 1 in row 3 because we have conditions A and C but not B. Or in other words, we'll have conditions A and C and the negation of B all being met. A times B times C. And our third possibility is if we have B and C being met but not A. In other words, we have the negation of A and B and C, and that occurs in row 5. So we've identified each case where we have 2 of the 3 parameters met, A, B, and not C, A and C but not B, and B and C but not A. So now any one of those 3 is okay, so we can combine these with a disjunction and say we want A, B, and not C, or A, not B, and C, or not A, B, and C. In other words, we're using Boolean addition. Let's go ahead and fill in that column with 1s and 0s based on whether we have one of these 3 conditions met. That is to say, this column, or this column, or this column. And there's our result. And we've done exactly what we were asked to do. We wrote a Boolean expression that gives us a 1 when we have 2 of the 3 conditions. Here we have A and B but not C. Here we have A and C but not B. And here we have B and C but not A. We got a 1 in the 3 rows where 2 of the 3 are met, but we got a 0 everywhere else. It's important to note here that this is the result that we're after. The Boolean table is just a tool for establishing our expression, but the question was create a Boolean expression. This is our Boolean expression that gives the desired result. Okay, so that establishes a foundation of Boolean algebra. You'll be given an assignment along with this in Blackboard. Make sure to complete that assignment, and we're going to build on these topics in our next class.